Good morning. So, we're gonna finish this poll placement, okay? And if we got time, then we can move on to another topic. Okay, in previous lecture, we have looked at a system like this, discrete state space model. Okay, and then what we do is we design a feedback for this U here, right? Yeah. So the choice of K basically determines the pole, closed loop pole location. Okay. Now, if you simply do this, this is what we call it's a regulation problem. Okay. So what does that mean? Basically, given any initial condition, okay, with a proper choice of K, then the state variable, the responsive state variable, all the state variables, they will all go back to 0, okay, given sufficient amount of time. Okay, so that's a regulation problem. But today we'll look at another one here, which is more general, basically problem. It's a tracking, essentially. Okay, it's a tracking problem. So tracking problem is, let's say you have y equal to cx of k here, right? Yeah. So y is the output. Okay. So the idea is basically given a reference input. So let's say we call that r of k at here. So what do we want? We want our y of k to follow this r of k, right? Yeah. So, and then objective is to have y of k, right, follow. Now since it's a single input, so I can just simply use a scalar quantity here, right, to have this guy follow r of k. Okay. Yeah. Now this problem basically is called reference tracking. Okay. So that's more a typical problem, right? Yeah. So how can we model basically our original pole placement, to have this objective satisfied? Okay, so here is the typical, basically, the diagram that you should implement in terms of the tracking problem. Okay, so here's a plant. So the plant is basically the state space model, which is a plant, right? Yeah. Then the plant output will multiply with that k quantity. Okay, so this quantity k here, and then the reference input is over here. So what we're going to do, we're going to multiply the reference input with a constant value k naught. Okay. Then we have this reference, the junction at here, so positive here and negative over here. Okay. So negative feedback, basically the negative is this negative sign here. Okay. Then give it to the plant, and then the plant output here is y of k. Okay, so this is what happens for this implementation of the tracking problem. Okay, and we'll see that if this is going to work or not. All right. Yeah. So this is basically your u of k at here, right? Your control input to the plant. Okay. So if I write down the u of k, so let's see what is the u of k equal to now. So u of k equal to negative k time, this is the state output from the plant. So negative k times x of k. So same as the previous pole placements, right? Yeah, the tracking, the regulation problem. But now you have one extra term at here, and that is k naught, times r of k. Okay. Yeah. So this is your new control input basically. Okay. Yeah. This K is the same kind of K as we had in the pole placement. So we designed this K. So this guy here, this is K is going to be designed or selected based on desired poles, okay, location, right? So you pick certain poles based on a desired kind of response, time, settling time, or damping ratios, okay, that kind of requirement. And then you can calculate the K based on the desired poles. It's the K naught we also have to take care of, okay? Yeah. The K naught is also scalar value. As we're gonna see later, okay, the K naught, okay, this K naught value, okay, we're talking about tracking problem. Basically what we're saying is we want the Y to be the same as the R, right? To be the same as R. So if I use step input, okay, as a reference, okay, then the output Y will be required to end up at this, let's say, step input magnitude is 1, then you're supposed to end up at 1 there too, right? Yeah. So the K naught is the idea is you have to calculate the K naught such that the Y of K will end up at this R of K. Okay, so that's what the K naught is supposed to do. Okay, yeah. In other words, the K naught needs to be adjusted. Okay, so when you use a referencing, when you use a step input as a reference, and your output is the same as the reference, and actually we learned a concept in the first lecture. How can we ensure that the output will follow the input? There's a concept which is called what? The DC gain, right? The DC gain of the system needs to be the closed loop system. Needs to be what? Do you remember? Yeah, it needs to be 1, right? Yeah. So that's basically how you should adjust the K naught here. So K naught needs to be adjusted such that, okay, this DC gain, okay, of this closed loop system needs to be 1. Okay. Yeah. So now, as you can see, actually, it's not too much trouble, right? Because you're doing exactly the same thing for the K. Okay. You're just doing one extra step to get the proper value K naught, right? Okay. So, but let's see what will be the other differences now. Here's the U of K, and here is our state space model here, right? So let's plug this U of K back into our state space model. It's basically like the feedback here, right? The feedback. Okay. So if I plug this quantity out here back into here, so what do we get? So we get this expression for x of k. Okay, so we get this expression for y of x of k here. Okay, yeah. Now you actually can see the idea now. So the idea is basically selecting the k here so that you're essentially make sure that the transient response will go back to 0. And then you select the K naught such that steady state value will end up at the desired reference input. Okay? Yeah. So let's use an example to illustrate that idea here. Okay? Okay, suppose that I have a system G is 0, 1, negative 1, 6, 1, negative 1. And H, it's this. C is this. Okay? Yeah. So your output basically is just the x1 of k, right? It's just x1 of k. Alright, so let's design this reference tracking problem here and then get the desired k and k naught. First step, generally you do is you probably just jump into the design here, but usually the first step what you do is you can check the controllability of the system given the system matrices, right? Controllability of the matrix is HGH, this second order. Okay, so you calculate this. This gives you 0, 1, 1, negative 1. Okay, yeah. So apparently this guy has a rank, right, equal to 2. So it's a full rank matrix. Yeah. So which means you can arbitrarily place any poles at anywhere location, right? Now let's suppose I'm going to desire my desired pole location, okay, is Z12 equal to 0.5 minus positive minus J 0.5. Okay, suppose this is my desired pole location. Okay. And we're trying to calculate the capital K, right? Okay, if this is the desired one, then this next step is what will be the desired, essentially, characteristics equation. So then the next is desired characteristic equation, and we use alpha CZ, right, as the symbol. Okay, and that's essentially the determinant of this quantity. Okay, yeah. Well, because we're given the desired pole location now, so the desired one, okay, is supposed to be this: z minus z1 times z minus z2, right? Yeah. Okay, so plugging z1 is let's say z1 is 0.5 plus j point, so 0.5 minus j 0.5, and z2 is 0.5 minus j 0.5. Okay, so that's the polynomial. So multiply this, expand it, okay, expand it out. You'll get z squared minus z plus 0.5. Okay. Yeah. Okay, so this is your desired polynomial, right? Okay, so now it's up to us to pick to calculate the gain matrix. There are different ways of doing this, okay, if you remember from previous lecture. But at the end of the last lecture, we presented a method called Ackermann formula. So let's try that one here, okay? Using Ackermann formula, what will be the gain matrix K? Okay. So Ackermann formula, if you recall that, what is Ackermann formula? So Ackermann formula basically saying that K equal to 0. This is the second order here. So 0, 1, and then time H, GH, inverse, and alpha C, G. Okay, that's Ackermann's formula. Yeah. So let's see, what else do we need to calculate now? We already have this HGH now, right? Yeah. So we can just simply plug it here, do an inverse. So we don't have alpha C of G yet. So let's see. Alpha C of G. So what do we do? Basically replace the Z here with the G matrix. Okay. Well, this is a scalar quantity 0.5. So once you replace the Z with the G, so you actually should multiply this 0.5 with identity matrix. Okay, so just make sure you have the consistent matrix size, right? Yeah. Okay, so G, you had it, just time itself, and minus G, and then plus this. So it's pretty easy to calculate. And then you will get this quantity. Okay, so you get this alpha CG. Okay. Okay. So everything you got it. So plug it into this formula here. Okay, you will get your K equal to this. Okay, that's your K. So which means with this K, you'll end up with the desired pose or desired characteristic equation as this. Right? Yeah. Okay. So the next step now is to make sure, okay, get the proper value K naught such that the system have DC gain of 1, or the system will follow the R of K. Okay? Yeah. So to get the DC gain, what we need to do is we have to derive the pulse transfer function of the closed loop system. Yeah. Okay. Here? Yeah. Rank basically is you look at the independency of the columns here, right? Yeah. Or rows. Yeah, because this is a 2 by 2, so it doesn't matter. So you look at the 2 rows or the 2 columns here. They're not dependent of each other, right? So the rank is 2. Yeah. Okay. Okay. So to get K naught, what we need to do is, let's say we need to get what is the pulse transfer function. Okay, of this closed loop system. So again, the closed loop system is this. Okay, this is a closed loop system, right? And you also have your y of k at here equal to c x of k. Okay, yeah. So pulse transfer function means what I wanted to obtain is I want to get this y of z over r of z, right? This is a closed loop pulse transfer function. Or in other words, you want to get y of z over r of z. Okay, that's what it means. Okay. So it's pretty simple. You know what you need to do basically. You can take z transform of both sides of this equation, and take z transform of both sides of this equation, right? Then you can get rid of that x of z and find a ratio between y of z and r of z, right? Yeah. So if you do this, okay, let's see if I temporarily I'm gonna let g hat equal to g minus hk. Okay, yeah. Just temporarily let g hat equal to g minus hk. Then the pulse transfer function will end up at c times, okay, zi minus g hat inverse, then times this hk naught. Okay, this hk naught. That's your pulse transfer function. You have all the basically matrices, okay? You have all the G, H, and K designed, except the K naught, right? So just K naught as a temporary variable here. So plugging all the values of the matrices, okay? And you end up with this fraction in here, and that's K naught, okay, Z squared minus Z plus, okay, 0.5. So that's your pulse transfer function. So pulse transfer function is the relationship between output and the input, right? Yeah. So what do we want again? We want the y to follow the r, basically. Yeah. And we set the DC gain to be 1. So DC gain meaning so basically DC gain basically means for this pulse transfer function you set z equal to 1, and then the DC gain, right, is basically 1. Okay, so basically you set this guy, you set z equal to 1, and that value, okay, should be 1. Okay, yeah, that's a DC gain equal to 1. Okay. That's pretty simple. Set z equal to 1, and this side here 2 k naught equal to 1. So k naught should be 0.5. Okay, yeah. So if you keep the k naught at 0.5, giving a unit step input, then the output, right, will end up at this value, unit step input value 1. Okay. So you can do a simulation to verify this this problem here. You see whether you really end up with this tracking problem, or if this desired pose give you supposed response of the system. Okay, yeah. So you can try it out. All right. So yeah. This is basically the definition of DC gain. Yeah. So the definition, if let's say this is a pulse transfer function, right? Maybe we can call this as what can we use? Maybe we can use I don't know. Let's call it d of z, right? Yeah. So the DC gain of any transfer function means you set z equal to 1, right? And you check what value you get. For example, if you have a of z over b of z, right? Then you set z equal to 1. So you're supposed to get something here, right? Yeah. If that value is not 1, so which basically means the input, the unit step response of the system, right, will not exactly end up at the 1. But if this value is 1, then you're guaranteed that the output of the system will end up at 1. Okay, or the same as magnitude of the input. Okay, yeah. Okay, so that's basically tracking it here. Okay, so later when we learn others, we're going to integrate actually this diagram into a bigger picture. Okay, yeah. So the second kind of control is called deadbeat control. Okay, or we can call it deadbeat response. So deadbeat control is a control that you do not see in continuous system, and this is basically specifically dedicated to this discrete time domain. Okay, so it's deadbeat control. So let's see what do we mean by deadbeat control here. Okay, yeah. So let's write this system equation again. So x of k equal to g x of k plus h, okay, u of k, yeah. And the y, okay, equal to c x of k. Okay, so let's say we're designing, okay, a response, okay, a pole placement. Okay, we're designing a pole placement here. Then the closed loop system, so I'll keep writing this, end up with g minus hk, okay, x of k. Okay, so as we learned, the solution of the system is g minus hk and time k, okay, x of 0, right, and x of 0. So without the rigorous proof, okay, one very extreme pole placement situation is if we can pick the k value, okay, such that the eigenvalue here basically means what? It's the poles, right? Yeah. Such that the eigenvalue are at the origin. Yeah, right. So do you remember in the previous lecture we actually was examining things. We were saying is, okay, so you have a response, maybe let's say z over z minus a. Okay, so that's the pulse here. So what does this correspond to again? It corresponds to a to the power of k, right? Yeah. So if I put this a as 0.5, it's 0.5k, right? If I put this a as a 0.3, it's this. If I keep reducing it, right? Yeah. So guess which one reduced to 0 in the fastest fashion? Which one go back to 0 more quicker? This guy here, right? So which means what? The closer to the origin, right? The faster the response. So that's why the extreme case. Shall we place the pole right at the origin? Okay. And what does that implicate? Right? So basically that's the idea of the deadbeat response. Okay, deadbeat response. So placing poles at the origin. Okay, at the origin here. To get the so-called deadbeat response. Okay, so more precisely, the description is x of k. So the deadbeat response is all about how fast you can bring the x of k from initial condition back to 0, right? That's the deadbeat response. So what happens at here now is x of k will go back to 0 for only a very limited number of steps. So for how many k, basically you say, oh, x of 1 is now 0, x of 2 it's not 0, oh, x3 is 0 now, right? So that's the idea here. So but how many k will experience then? The k will not experience too many actually. The k will supposed to be greater than a value, but this q will be less than n, the order of the system. Okay, the order system. So if you place the poles at the origin, and the state variable x of k will go back to 0 in the maximum steps, which equal to the system order n. If you have order 2, system order is 2. So that means the maximum it'll take to go back to 0, the number of steps, is only 2. Okay, yeah. So that's the idea. Now, what does placing the pole at the origin means? Placing the pole at the origin, basically, what does it mean? So it means what? It means the desired characteristic equation, okay, of the polynomial of the system, that zi minus z minus hk, this guy, what does it become? The polynomial. This is a desired polynomial. It's supposed to be what? It's supposed to be z minus z1, z minus z2, and z minus zn. So it's supposed to be this. But now you place all the poles to the origin. So this is supposed to be given with only z to the power of n, right? Yeah. So now this is your desired polynomial. Okay. Yeah. Okay. So that's the guideline here in terms of designing the deadbeat. So let's take a look at example now. Okay. Okay. Let's take an example. So I'm going to try to design a deadbeat response for the double integrator. So if you remember, in previous lecture we had a double integrator, right? Yeah. Okay. Yeah. So you can also design the basically deadbeat for the reference tracking problem. Same thing. So because you see everything that we're talking about here is just selecting the k, right? If I modify this a little bit here, just like the reference tracking, put it as R, sorry, key not and R of key like this. The same idea. Oh, you mean which one would you prefer? Well, you'll see it actually. Yeah. That's the question. Yes. Yeah, that's the question. So, which is what I want to demonstrate through this example here. Yeah. So let's look at this system, the double integrator here, 1 over s squared. Okay. Yeah. In the previous lecture, we discretized the system and we did a pole placement for the double integrator, right? We can arbitrarily place the pole for this double integrator by picking up a proper K gain matrix K, okay, and the K gain matrix K is K1 and K2, right? K1, K2. Okay. So if you look at the lecture notes, okay, you will see that the gain matrix K1, okay, equal to 1 over T squared, okay, 1 plus P1 plus P2, and K2, and equal to 1 over 2T, okay, 3 plus P1 minus P2. So P1, P2, they are the coefficient of the desired polynomial. So let's say alpha CZ is Z squared plus P1Z plus P2. Okay, so this is a desired, whatever your desired polynomial is. Okay, yeah. Okay, that's what the results that we end up with from previous examples in the previous lecture. Okay, yeah. Okay, so now let's suppose what your desire to do is you wanted to design a deadbeat control. Okay, deadbeat control. Okay, so T at here is sampling time. Okay, T is the sampling time. If I choose deadbeat controller, which means the P1, P2 will be 0, right? Will be 0. So then the K1, K2, right? So for deadbeat, P1 equal to P2 is 0. So that means the K1 will equal to 1 over T squared, and K2 equal to 1 over 2T. Okay, 1 over 2T. So that's your gain K1, K2, which actually depends on what? Depends on the choice of sampling time now, right? Choice sampling time. Okay. So let's keep the T there, and then we'll vary the K to a different value. We'll observe the differences. Okay. Yeah. So this is a K1 and K2. So that closed loop system is G minus HK, okay, X of K, like this. Okay, closed loop system. Okay, maybe I'll bring that lecture here. Just this is the double integrator I was talking about here. Okay, and this is the G, H, and the matrices. Okay. After discretization, this is what you get. Okay. Yeah. Okay. So now I have the K. So K matrix is 1 over T squared, 1 over 2T. Okay. And H is this. G is this. All right. Yeah. So then let's plug everything back into here. Right. Keep the sampling time. And you do a little bit simplification, and you'll end up with this quantity. So 1 over 2, 1 over 4t, negative 1 over t, negative 1 over 2. Okay, and that's the deadbeat design. Okay, That's based on the deadbeat response here. So now let's verify. Suppose that my initial condition is this. Okay, so initial condition is this: 1 and 1. Okay, yeah. If this is the initial condition, then let's check what will be the response of this state variables. Okay, what will be the response state variables? So we'll look at the step by steps. Okay, step by steps. So first, let's check. Okay, for sampling time equal to 1. Okay, let's check sampling time equal to 1. If sampling time equal to 1, let's see when k equal to 1. So started, right? You started from the first step. When k equal to 1, and what will be the response? So what do you do? Basically, when you k equal to 1 here, this is what? X of 0, right? It's x of 0. So basically 1 over 2, t equal to 1. So 1 over 4, negative 1, negative 2, then you time 1, 1, initial condition. Okay, initial condition. Okay, so this matrix multiplication give you 0.75, negative 1.5. So it's nowhere near the 0 point, right? It's nowhere near the 0 point. Okay, so let's keep one more step at here. X of 2. Okay, x of 2 here. X of 2 is the same matrix. Then time 0.75, negative this. Okay, same matrix. So now if you use your calculator, okay, what would you expect? Actually, you should think about the statement I was saying here. Yeah, I had a statement right here. When you design the dead response, basically place the point at the origin here. You're supposed to get this x of k go back to 0 for a maximum number of steps is the system order n. So here it's 2 now. So you're supposed to be 0. Okay? If you don't get a 0, there's something wrong. But then you plug it and you see it's 0. Right? Yeah. Okay? So that essentially sort of verification, right? And then you can keep going. You can check x of 3 and keep going. They're all going to be 0, right? Yeah. Okay. So now let's see the question here to verify the realistic, sense of this deadbeat response. If t equal to 1, right, then let's check the corresponding control input. What will be the value, okay, or what will be the quantity of control input to the system? And control input is u of k, right? It's u of k. So I guess what we can do is we can check, each steps basically, okay, for the control input, okay, for the control input. If you recall that from the previous lecture, okay. So not really here. So let's see, what's u of k? U of k equal to negative k time x of k, right? That's u of k. And what is the k again? K is 1 over t squared, 1 over 2t. Negative x of k. Okay? Yeah, that's your u of k. So apparently you can see your u of k is going to be a function of the sampling time, right? If you change to a different sampling time, your control input will change, essentially. Okay. So let's see. I'm going to pick 3 different sampling in times here. Okay. Yeah. First, let's see I'm picking t equal to 10 seconds. Okay, 10 seconds. For t equal to 10 seconds, and t equal to 1 second, like the previous, like what we just did, and t equal to 0.1 second. So for t equal to 10 seconds, let's say what's the value of u0 starting from the first step, right? u0. So what is u0 equal to? u0 equal to what? This quantity time x of 0, right? x of 0. And now the t is 10 seconds. So t is 10 seconds, meaning this is negative. And then 1 over 100, 1 over 20, and time 1, 1, right? And 1, 1. Okay? Yeah. So then this quantity will equal to negative, okay, 0.16. Okay, negative 0.16. Yeah. And now, when t equal to 10 seconds, okay, and you can keep multiplying it here. Then u of 1, yeah, what is u of 1 equal to, right? Yeah, keep going. So same gain time the next. This is not a response for t equal to 2 seconds, but I guess you can calculate the value for response of t equal to 10 seconds, huh? Yeah. But anyway, I think you're gonna end up with, I don't have it here, this guy here, okay? 0.06. Okay, this here. Okay. Oh, the first one is? Oh yeah, you're right. So where's the negative 1.6 from? Okay. So what is this equal to? Anyway, let's check here. But the idea is let's take a look like t equal to 1 second here. Okay. So if t equal to 1 seconds here, what is u of 0 equal to? And this is going to be 1 half, good point, and 1 1. So what is this equal to again? So 1 times 0.5. So it's negative 2.5, right? So negative 2.5. Okay. So let's cross this out here. Okay. Not sure where that's from. So what will be the next step? The next step is 0.75, 0.5. So this one I have it here. Let me verify if my lecture notes right. 0.75, 0.5. Sorry, was it? Negative. So what does this give us again? This one negative, no, positive. Here, this is positive. So positive 0.75. Positive 0.75 plus, that's a negative 0.75, right? So it's actually 0 now, right? Yeah? Yeah. So how about t equal to 0.1 seconds? What about the u of 0? You plug the t equal to 0.1. So this is 1 over 0.01, 1 over 0.2. Okay, so this is pretty big. This is 100. That's a 50, right? No, that's 5. This is 100. This is 5. So together, negative, was that right? Yeah, 105. Okay, yeah. So, if you do a quick comparison in here, just compare the u of 0, right? Just compare the u of 0. As your t is getting smaller, so basically, which means you have a the duration is smaller now. Your u is increasing rapidly, right? If you use a 0.01, guess what? I think it's going to be really big. So that's basically the point here, the deadbeat response. If you want, well, 10 seconds is generally not that realistic. So you want to, basically, because your sampling time needs to be able to satisfy the sampling theory, right? But at the same time, you're at the expense of having a very high control input to the system. Okay, yeah. So that's why the deadbeat response, okay, a lot of the time it's not very realistic, right? Yeah. Unless you have unlimited power as the input. Okay, yeah. But it is mathematically feasible, though, right? Yeah, or doable. Okay, so check this location here. Any questions? Yeah.
Back to the beginning of the example, where did the original equations for K1 and K2?
This is basically from it's the same idea from the derivation of the pole placements. So let's say, for example, here, right? This is a double integrator. This is a discretized result. This is the pole placement formula, right? Yeah. So we plug this one into the state space model here. We end up with the closed loop system as this, right? Yeah. And then the characteristic closed loop system is this. If for pole placement means you want this characteristic equation, the closed loop one, to be the same as a desired characteristic equation. In other words, you want this coefficient same as this, this coefficient same as this. So two equation, two unknown. You can solve for K1, K2, which is what I listed there. Yeah. Okay. So that basically wrap up this pole placement concept here, right? Yeah. You actually in the lab visit, as you can see, how easy it is to implement a pole placement control, right? Yeah. You can try it out yourself, but I think you do need another little bit of knowledge is how do you pick the poles, right? You pick the poles needs to satisfy certain time response specification, right? Yeah. It's not you can arbitrarily, of course, yeah, right? But there should be something bear in mind is that pose corresponding to certain set of response that you are looking for, right? Yeah. So this actually brings us to the next thing here is if you really wanted to know what kind of response that pole will give you, right? We typically what we do is, if I ask you the same question, here's a continuous system. You have this transfer function of the continuous system, right? Yeah. So the question is, if you look at, oh, look, this is the pose of the continuous system, right? Yeah. Second order, for example. Okay. Then, if the same question asks you, can you visualize what kind of response the system have, right? The system has, given the current pose of the system. I think it's probably easier for you to answer because it's a continuous system. Then you can look at the tables, look at or diagrams. You see, oh look, the pose out here, the response is supposed to be like this, and the pose here is supposed to response like this, right? Yeah. And there's always, remember the two formulas that I give you to you in the first lecture. Basically relates the damping ratio, natural frequency to certain design specifications, right? Sampling time, overshoot, percentage overshoot. Now, so basically the idea is, let's look at the mapping, right? From S-plane, okay, to Z-plane. Because where does the pose of the Z-plane from? It's mappings, actually. Ultimately, your discrete doesn't come out of nowhere. First you have this continuous signal. Then you did a sampling here, right? You do a sampling, impulse sampling. Then you get a whole bunch of impulses, right? Okay, yeah. So that's called impulse sampling, right? Yeah. So the response of this continuous signal can be characterized by the response of these discrete numbers, right? Discrete numbers. Okay. Over here you have the S pose. Over here, what dictates the response is the Z pose, right? So for example, this side here maybe is S plus 1, right? What's S plus 1? It's e to the power what? Negative t, right? E to the power negative t. And what about this side here? After you do a sampling, this e to the power of t becomes e to the power of kt, right? E to the power kt. Okay? Yeah. And then you'll get maybe z minus z something at here, a pole, right? Yeah. And how does a pole? What's this pole here now, right? What's this pole value? And that value, if you recall that, okay, this guy here basically, this in this case I think it's just this guy here is gonna be what? This is e to the power of negative t to the power of k, right? So what should I have it here again? Okay, e to the power negative t. Okay, yeah. So the idea basically is, you have a response. You know the response is dictated by the location of the pose. And if I really wanted to characterize the response, and I can always go back to the continuous system. Look here, this comes from exponential decay, and how does a mapping? This is the mapping goes. This is the direction how it goes here, right? The direction goes. Okay. Yeah. And as a matter of fact, if you remember, when you have an impulse sampling, okay, when you have an impulse sampling for a signal, the relationship between Z and S is this: Z equal to e to the power st. Okay. Yeah. So basically, whatever the S-plane pose at here will be mapped, okay, through this relationship, right? Based on our this is a long time ago the lecture now, right? Yeah. Okay, so let's look at a couple of just kind of to jot your mind here, right? Just sort of maybe I can consider this as sort of the case number 1. Okay, when you have a simple pose, right? This is when you have a simple pose. That's how the mapping will go, right? How the mapping will go. We can maybe use a more generic case here. If this location is B, it's BT. So after sampling, you get negative BKT, right? Then e to the power negative KBT, the Z transform is Z over, okay, Z minus e to the negative BT, right? Negative BT. Because this is basically like this. It's like a to the power of k, right? A to the power of k. Okay. And we also have dealt with a more sophisticated or more complicated, which is a complex pose. Okay, if it's complex pose. Now the complex pose for continuous system, for continuous system is sigma plus minus j omega, right? Sigma plus j omega. That's your complex plane in continuous domain. Okay? And when you have a complex pole in continuous domain, then let's say maybe what you have here is this. So second order system. So s minus sigma square plus omega square. Okay, so what you have maybe is this guy here. So you look at the denominator. The poles of denominator give you is basically sigma plus j omega. Okay. Yeah. Now, if you remember, what will be the inverse Laplace transform for this guy here? And it's actually e to the power of sigma t sine omega t. Okay, sine omega t. If we do a sampling, if we do an impulse sampling here, okay, if we do impulse sampling, then the continuous signal becomes e to the power of sigma kt, okay, sine omega kt. Okay, yeah. All right, so then the question is, what's the Z transform of this guy here, right? So Z transform this. Okay, yeah. I mean, you look at your Z transform table, you will find it out. Okay, and this one here, the Z transform, give you this quantity, e to the power sigma t, okay, time sine omega t times z over z square minus 2 e sigma t z cosine omega t plus e to the power of 2 sigma t. Okay, you end up with this Z transform. Okay. What about the poles of this Z transform? Right, the poles of Z transform. If I don't like the e, I can actually do a little bit of simplification here, because what we can do is this. For this quantity here, we can write it as e to the power of sigma t to the power of k, right? For that quantity. So I can let e to the power sigma sampling time equal to a. Okay, so I can you can let it equal to a at here. So this is a to the power of k, sine omega kt. Okay, so same thing. So just replace the e to the power sigma t with a. But either way, if I'm interested in the pole location of this this Z transform, Z squared minus 2a cosine omega t times Z plus this is a squared. Okay, it's a squared. So you set this guy equal to 0. Okay, solve for Z. Okay, solve for Z. That's the poles. So this is the poles of the continuous system. And what will be the poles of the Z, the discrete one, right? Discrete one. Okay. So you actually will find that the poles of the system, right? Z equal to, it's a complex poles, of course. Okay. So you can use the Z equal to z to the power of st, okay, to find the mapped pole, okay, to find the mapped pole. But what you're going to find is essentially this, okay? So a times cosine omega t plus minus j sine omega t, and equal to a is e to the power positive negative omega t. Alright? Yeah, that's what you're going to find. Okay. Yeah. What's a again? The a is e to the power sigma t, right? Yeah. So if I do same thing from here, if the let's see if I can do a quick verification here, st. If s is sigma plus j omega, t, right? So what does that give us? See, that it's the same thing, right? It's the same thing. Okay? Yeah. And that's in the format, you can write it in the format like this, right? R value theta. Okay? R theta. And what's the theta? Theta is omega t. Okay? Theta is omega t. What's R? R is for the magnitude. It's e to the power sigma t. Okay? Yeah. Okay, so that's the mapping. Basically, when you have a continuous pose, okay, and the continuous pose cause certain kind of response, and with the impulse sampling of a certain sampling time, you end up with another response, right? And that response is turned by this Z pole, and that Z pole, okay, can be obtained through this formula. Is that good? Okay, good. That's the fundamental idea of the mapping. Okay, so we're looking into essentially more details, okay, of the mapping. Okay, yeah, probably in the next lecture. But before we do that, there's another concept I wanted to talk about, is the natural frequency. Okay, so natural frequency in time domain and in Z domain, in discrete domain. So basically in the continuous domain and in the discrete domain. Okay, so let's think about the natural frequency concept. So I'll start with a very simple one here, sine omega nt. Okay, sine omega nt. So this is a sinusoidal function with a frequency of omega n, right? Omega n. So if the question is simply asks you, what's the natural frequency of this signal? Then what is it? Omega n, right? So omega n. Okay? Yeah. And the period is 2 pi over an omega n, right? Period. Instead of sampling, so let's call it just period here. Okay? Yeah. Okay, so now let's do a sampling. If I sample this guy now, if I sample this, so sampling it, sine omega n kt now, right? Sine omega n kt. Okay? Yeah. So sine omega n kt. So basically, if I draw a sine here, okay. Let's see, keep drawing a few more. Your t is the sampling time. The sample you get it here is separated by sampling time t, right? Sampling time t. Okay? Yeah. So if the question is this, can you calculate what will be the total number of samples per period? So here's this continuous system. After sample, it's not going to be a curve anymore, right? It's going to be a sequence of numbers or samples. So here is what will be the total number of samples, okay, per period. How do we calculate that? I know the period is 2 pi over omega n, right, for this original continuous sinusoidal signal. And I know the samples are separated by how much? Sampling time t. So guess what? What will be the total number of samples? You have this much period. You have samples separated by t. So what do? We use the period divided by the intervals, right? Yeah. So that's the total number of samples per period. Okay, per period. Okay. Yeah. Okay. So, and the next thing here is, okay, what does this n, the total number of samples per period, mean? So this actually means the discrete signal. Okay, the discretize the sampled signal, they will repeat, okay, themselves at every n number of samples. You see what I'm saying, right? They will repeat themselves every n number of samples. Say for example, if you do this one here, you do 1, 2, 3, so there are this much samples here. It'll repeat this 6 here every this n much of here, right? They will repeat every n number of samples here. Okay? Okay, every n samples. If this guy gonna repeat every n samples, you know, our sample time is sine omega ntk. Okay, this is the sampled signal, and we know that. So look that for any sinusoidal signal, okay, you know, if you plug a 2 pi, it doesn't change, right? Yeah. So now if I do a quick modification here, if I take the omega nt out, then inside here is k. So k times what? K times 2 pi over omega nt. Okay, 2 pi over omega nt. So what do we end up with? What is that 2 pi over omega nt? Which is the number of samples here, right? See that? Okay, number of samples. So previous continuous signal, you repeat itself every 2 pi, right? Every 2 pi. And now it's repeating every n number of samples n. Okay, n here. Okay. So this n here is like the period, but it's not the period. Okay, yeah. We're saying the natural frequency. The natural frequency in continuous domain, time domain, is omega n. So right now in the discrete, in the z plane or the discrete plane domain, what's the natural frequency? The variable is not time anymore. The variable is actually instant k, right? So the natural frequency becomes this one now. Okay, omega nt. Okay, so theta equal to, I'm gonna let theta equal to omega nt is the natural frequency. Okay, it's natural frequency now. Okay, in z plane or in this discrete domain. Okay. What will be the unit for theta? Unit for theta will be what? So first of all, overall inside this big bracket, the unit for everything inside the big bracket should be reading, right? Should be reading. It's angle, right? Should be reading. Okay. The unit for k plus n, what are they? They are samples, right? You know, number of steps, samples. So the unit for omega nt should be reading per sample. Okay, reading per sample. All right. Yeah. Okay. So I want you to bear in mind of this theta is the natural frequency here. Okay. So let me give you some diagram here to give you some sense regarding this the sample things here. So let's see an example. Okay, I'll use cosine instead of using sine in my graph. I use the cosine omega n t. Here's my continuous signal. Okay, here's continuous. So we're sampling it. Cosine omega n kt. Okay, yeah. So let's say my omega n is pi over 8. Okay, this is the natural frequency of the continuous signal. Okay, continuous signal. So we're starting to sample this now, right? Yeah. So we're going to sample this at a different sampling time. So t equal to 1, 2, 4, and 8. So maybe start with t equal to 1. So when t equal to 1, what do we end up with? Cosine what? This omega is pi over 8. So what do we end up with? Pi over 8k, right? And when t equal to 2, we end up with cosine what? Pi over 4k, right? Pi over 4k. And when equal to what was it? 4, it's a cosine pi over 2k. If t equal to 8, what is it? Pi k, right? It's pi k. Okay? Yeah. So at a different sampling time, you have a different sequence of numbers going to be generated, right? But you also have to think the way you're sampling it. Okay? The way you're sampling it is, this is your cosine here, right? It's your cosine. You're sampling at a different time instance. What was it? This is a pi over 8, right? This is a pi over 8. If this is a pi over 8, what was this value here? Times that. Sine here is sorry, what was it? When t equal time t, when t equal to this is supposed to be pi over 2 when t equal to 4, right? Isn't it? This is 4 here, right? When t equal to 4, this is pi over 2. Huh? Yeah. When do you get, this is 16, right? This is 16. And this is 8. This is 12, right? Yeah. So when t equal to 4, 8, 12, 6, that's one period, right? Yeah. So right now, if you're sampling with the t equal to 1, so what do you end up with? You basically, there's some number of samples, right? But if you're sampling with, let's say, t equal to 8, guess what do you have? 1 and here, 1 and here, 1 and here, 1 and here, right? Okay. So, but you also should be aware of this. When you do the sample, when you look at this one here, it looks like the sample is separated by this much distance, right? But after the sample, all you do is what? You put all the sample together. Basically, when you do, you put that sample here, 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 here. You don't really care what's the original distance between two samples. All you need to say, this is a number 1 sample, number 2 sample, number 3 sample, number 4 sample, like that, right? Yeah, that's what you call a sequence of discrete signal, right? Yeah. So after sample, you basically put them together and label them as the number of instances. Okay? Yeah. So this is what happens if I plot this out. This is what happens with the sampling, okay, of this. Okay, first one is t equal to 1, t equal to 4, t equal to 2, and t equal to 8. Alright? Yeah. So number of things. So first of all, tell me which one do you think has a higher frequency? T equal to what? 8. Why is it? Because it goes here, here. That's finished one period, right? For this one. Then it goes again. That makes sense, right? This one has the highest frequency. As a matter of fact, what is the cosine pi k? What does the cosine pi k equal to give it to you? What is value cosine pi? Cosine pi equal to here -1, right? And what is cosine 2 pi? It's 1. So this is actually 1 to the power of k, right? 1 to the power of k. So this guy has the highest frequency. But if the question asks you this, which one has a better description of the regional time signal? This guy here, right? So that actually basically, it's the idea of the sampling time. Your sampling theorem, your sampling time needs to be faster enough to reconstruct the original one here, right? But here what we're talking about is the natural frequency of the discrete signal. Natural frequency discrete signal is omega nt. Okay, so omega nt. In this case here, omega n is pi over 8. Then at a different time instant, you have a different frequency. And the frequency is the highest one when this is when theta equal to pi, right? This is when theta equal to pi. And this is when theta equal to pi over 4. And this is when theta equal to pi over 2. Okay? Yeah. Now can you imagine this? Will the frequency be faster than this guy? Is it possible to be even faster than this in the discrete domain? Not at all, right? All you can change discrete domain is this: up and down, up and down. How can you be faster, right? Yeah. So that, having said that, basically saying is, in a discrete domain, that the frequency is so different now. In the time domain, I can increase the omega n to faster the angular frequencies, right? But in a discrete domain, when you see the samples, when you're talking about samples, natural frequency samples, the fastest that you can go is what? Theta equal to pi, or theta equal to negative pi. Okay, yeah. That actually we'll do when we do the next. We'll learn a little bit more there. Essentially, we'll have a unit circle. The change of the theta is from here to here. Okay, it's from here to here. So over this range, when theta varies between here, it's what we call low frequency. But over this range, between negative pi to pi, it's called high frequency. So like this. Alright? Yeah. Okay, so we'll continue on this mapping in the next lecture. Okay? Yeah. Next week,